Hello guys, my name is Balakrishna Srivastava and welcome to Code with PK. So in this video, we write a Python program to check if an integer n is a prime number or not. And this question is also listed in the list of suggested Python practical programs for CBSE Class 11, Class 12 Computer Science students. So this is a handy program if you are a CBSE Class 11, Class 12 Computer Science student. So before we begin, it is a request to please subscribe to my channel, because out of 100 viewers, only 2 to 3 are subscribed. More than 95% of my audience is not subscribed, and a subscription is very important. So please do subscribe to my channel. And I also teach coding in Hindi on a separate Code with BK Hindi channel. So if you are better comfortable with Hindi, you can find a lot of content there on my Code with BK Hindi channel as well. The link for the channel you can find in the description of this video. And all these questions, okay, all these Python programming practice questions also for Class 11, Class 12 CBSE Computer Science students are already solved in Hindi on my Code with BK Hindi channel. You can find the link of the playlist and the channel in the description of this video. Please check it out. Okay, so let's begin. So we have to check if an integer n is a prime number or not. Okay, so we all know prime numbers. Okay, if I want to check n for prime number, a prime number is a number which is divisible by 1 and itself only. Okay, for example, if I take n equal to 9, it is divisible by 1, 3 and 9. So there is a number apart from 1 and this number n itself that divides n completely. So this is not a prime number. Okay, then if I take n equal to 7, okay, it is divisible by 1 and 7 only divisible by 1 and itself. So this is a prime number, and this is what we need to check. So we see two approaches to solve this problem. We see first the brute force approach, where we make no optimizations. In the second approach, we make a lot of optimizations and reduce the runtime significantly. Okay. All right. Now suppose if I need to check if n is 10 and I need to check if it is prime number or not. So all I need to find is a number between 2 greater than 1. Okay. So let's say I is a number that I have to find greater than or equal to 2 and less than n that completely divides n. Okay, if I find that number, it means I find a factor of n apart from 1 and n itself. It means it is not a prime number. Okay, it means it's a composite number. 1 is neither prime nor composite. Okay, so for the case of 1, is simply return false. So let me just start the code as well. Okay, so I'll say def prime 1, okay, takes an integer n. Okay, so if n is 1, we simply return false. 1 is neither prime nor composite. So 1 is neither prime nor composite. Okay. Approach 1, brute force. Okay. Okay. We need to find a factor that completely divides n. So what we can basically do is iterate from 2 to less than n. Okay. And in each iteration we pick up the value I, check if I divides n completely. It means n is not a prime number. If you are not able to find any value of I that completely divides n, it means n is a prime number. Okay, and we can use percent modulus operator to check for divisibility. A%b returns the remainder when a is divided by b. So the remainder will be 0 when a is completely divided by b. So if I have, say, a%b returning 0, if I equate it to 0, this condition being true means a was completely divided by b. It means b is a factor of a. So what we need to check is n%i equal to 0. That is, I should be a factor of n. Okay, so first thing, generate I, which is equal to this range. Okay, greater than or equal to 2, less than n. And b, check if I is a divisor. Okay, completely divides. Okay, so going back to the code, so generate values from 2 to less than n. Okay, that's what we discussed. The values of I that we need to generate are 2 to less than n. Okay, so for I in range starting with 2 less than n. Okay, if I divides n completely, return false. Okay, so how do we check that? If n%i double equal to 0, I divides n completely, I return false. Okay, finally I return true. Now I return true because I was not able to find any value of I that completely divides n. this condition was never true for any single value of I, it means we have not found any divisor of n apart from 1 n itself. Okay, because we are not including 1 and n itself in the range. Okay, so this loop did not return false, so you eventually return true. Okay, yes, this is a prime number. Okay, all right, so let me just check this out. Find prime numbers between 1 to say 40. Okay, for I in range, say start from 1 till 40, less than 40, so less than till 40, so less than 41. So if this is a prime number, so if prime 1 pass the value of I returns true, okay, this condition is true, I'll say print if I is a prime number. Okay, right, print all the prime numbers between 1 to 40. So let me run this. I'm gonna bring myself here. Okay, so 2 3 5 7 11 30 17 19 23 29 31 37. You can increase this to 101. Okay, so we'll have prime numbers between 1 to 100, and that's what we have. Okay, and this is your brute force approach. Okay, moving on to an optimized approach. Okay, so I'm going to write def prime 2. Okay, the idea remains the same, we just optimize a little using a little coding and maths. So optimize approach 2 is optimized. Okay, now how do we optimize this? So the idea on which we are writing this code is checking if we can find a divisor and generating all possible values that can be a divisor. Okay, so we can make a major optimization here by reducing the number of values that are possible candidates for a divisor. Now how? For example, n equal to 10, I am generating values greater than equal to 2, less than 10. Okay, greater than equal to 2 and less than 10. So these are the values I'm generating, and I'm checking if any one of these values divides n completely, which is 2 in the first case, in this case. Okay, what I can do is first eliminate all even numbers. That is, any even number apart from 2 is not a prime number, or you can say 2 is the only even prime number. Okay, so we, apart from adding a case for 1 here, okay, 2 is the only even prime number. So we take the case for 2 separately. We say if n equal to 2, return true. Okay, any other positive even integer apart from 2 is not a prime number, because it already has a factor of 2 apart from 1 n itself. Okay, so if we then apart from 2 find a number that is even, that is completely divisible by 2, okay, we return false. Okay, by doing this we have eliminated all the even candidates. Okay, then since we are eliminating all the even candidates, rather than starting from 2 going to less than n in increments of 1, we start from 3. Okay, I will start from 3, go till less than n increments of 2. That is, this was I 2 3 5 6 7 8 9. This will be starting from 3 in increments of 2. Okay, 3 5 7 9, removing 4 6 and 8 and 2. Okay, although this will already be eliminated because n% 2 equal to 0. Okay, for 10, so this will be returning false. Okay, let's take another example, n equal to 15. So initially in the brute force case, you would generate values 2 3 4 5 6 7 8 9 10 11 12 13 and 14. Okay, in the optimized case we want to get rid of the even values. Okay, so we start generating from 3 in increments of 2. Okay, so I can copy this loop. Okay, the idea remains same, it has to divide n, right? So but in this case start iterating from 3 in increments of 2. Okay, start iterating from 3 till less than n in increments of 2. So 3 5 7 9 11. Okay, if any of that value divides n completely, it is not a prime number. Okay, all right, we can further reduce these number of values that are being generated. Okay, now this involves a little maths because we are going till less than n. Okay, we go till from 3 to less than equal to sqrt of n square root of n and not n. Okay, so the second optimization is iterate till less than equal to square root of n. Okay, now why we are doing this? Now suppose if I have this integer n, right, and it is not a prime. Okay, if it is not a prime, it has a factor say I, okay, which is greater than equal to 2 and less than n. Okay, not a prime number. So this condition should be true. Now if this condition is true, that it has a divisor greater than equal to 2 and less than n, it means n% I equal to 0. Okay, for some value I in this range. Okay, if this is the case, we can say when you divide n by I, you get a value m. Okay, this is percent operator. It means I is completely divided by n, dividing n, but when I is completely dividing n, we get the quotient m. Okay, from this we can say, okay, from this we can conclude n is equals to m into I. So this is one equation I have. My second argument is m I both cannot be greater than, okay, square root of n. Okay, why? Because if they are both of them greater than square root of n, then m into I will be equal to some value greater than square root of n into some value greater than square root of n, which will give you a value greater than n. Okay, so if both of them are greater than square root of n and you multiply them, you are multiplying two values that are greater than square root of n, so the product that you get will be greater than n. So this inequality will not hold. So we can conclude that both of them cannot be greater than equal to n. So m or I within one of I, one of them is less than equal to square root of them, one of them. Okay, so you can always find a factor for a composite number, non-prime number less than equal to square root of n, where for n you are checking from prime. Okay, so for a composite number, okay, a divisor or a factor, you can say, either exists for less than equal to square root of n. Okay, so one final optimization is rather than going till n, we can say going till sqrt square root of n. So import math, right, import math, okay, and go till math dot sqrt of n plus 1 equal to square root of n. Okay, since square root will be returning a float, you can convert this into int. Okay, because this has to be an integer for the range for this for loop to work. Okay, so we changed our range from this to this. The number of times this loop runs significantly reduces. Okay, and then finally we have to return true, just as you were doing in the previous case. Okay, so you see the idea for both are the same, that you have to find a possible divisor for this value n. If you're not able to find any possible divisor, it is a prime number. Okay, we just optimize by taking the case of 2 separately, eliminating all the even cases out, and then reducing the number of times this for loop runs. Okay, all right, so checking prime 2 now, this should give us the same output as prime 1. So running this now, okay, 2 3 5 7. Okay, so we can check this by saying if prime 2 is not equal to prime 1 of I, okay, we can say error at I. Okay, that is both the functions are giving a separate return value for a given value of I. This should not be happening, so we should not be getting any error at all, and we can simply finally say done. Okay, so clear, we just get done. Let me make this, okay, done, no issues at all. So both these work exactly the way we want. Okay, all right, I hope you were clear with this maths here. If you want, I can share a link in the description that explains why we go till square root of n and not till the entire range of n. Okay, but the explanation in short is what I did. Okay, is what I explained here. Okay, also if you want to check for composite numbers are numbers which are not prime. So you can write a function def is composite or composite. Okay, takes an integer n. Okay, this basically will use the prime number function. So if the integer is not a prime number, it is composite. If it is a prime number, it is not composite. So you just have to return not prime 1 and you pass n. Okay, and you can take the case of n equal to 1 separately, return false. Okay, because 1 is neither prime nor composite. So for 1 this will return false, and then it becomes true for composite if n equal to 1, right? We don't want that. So for n equal to 1 you return false, otherwise you return not of prime. Okay, if it is not a prime number, it is composite. Okay, prime 1 or prime 2, whatever you want. Okay, so to check this we can say if number is prime, it is not composite. If it is composite, it is not prime. Okay, so if it is a prime, it's composite and pass I. Okay, this should not be the case, but if it is the case, I say print error at I. Okay, so running this now, done, no issues. Okay, so this was your Python program to check for a prime number, and also you can use the same to check for composite number, right? Okay, so I hope you like this video and this was helpful. So if there is any doubt, there's a part you don't understand, please let me know in the comments. I always try to answer all your comments. And you can also let me know in the comments if there's a question you want to solve or with the concept you want to discuss. So please like this video, subscribe to my channel, and thank you for watching.